Hi, welcome to class. In the last video, we saw how to use variation and parameters to find a general solution for first-order linear ODEs. In this video, we're going to take a look at some examples, but it won't make any sense unless you go watch that last video, so I'd recommend starting there if you haven't seen it already. Otherwise, let's jump in. Alright, quick recap. Last time, we saw if this is a linear differential equation, then the general solution is just the complementary solution, which is what I get when q is 0, plus the particular solution, which is what I get when I variate parameters. Let's use that to solve this linear ODE. But before we get started, I want to make a game plan for this because I think we can do it in 4 key steps. The first step is, I guess, kind of subtle, but do you notice I have the equation written in standard form? So I should start there. I should start with standard form so that all of my formulas work for me. Then I need to find yc, then yp, and then add them up. Now, that might seem a little silly to do first, but I like to write my game plan because, as you'll see in a minute, it can get into the weeds on computation, and it's good to have this written down from when my head was clear once I get down into the thick of it. So let's get started. Step 1. We need to write it in standard form. And remember, all that really means is make sure that the y prime has a coefficient of 1. So in this case, I've got a coefficient of t, meaning I actually have to get rid of that by dividing everything by t. So if I divide both sides of this equation by t, I get y prime plus 2 over t y equals t minus 1 plus t to the negative 1. And now you can see a little bit more clearly that here I've got my p of t, and here I've got my q of t in the standard form. Let's get started on step 2. We need the complementary solution, which is the easier of the two to compute. Let's get started. The complementary solution, in this case my variable's t instead of x, is going to be a constant times e to the negative integral p of x dx. Or, I guess I should say, t. Now, if I plug in p, I get the integral of 2 over t dt. That's just negative 2 natural log of absolute value of t. That's natural log of absolute value of 1 over t squared. 1 over t squared is always positive, so I can drop absolute values, cancel natural log, and I just get c over t squared. There's my complementary solution. Let's do the particular solution. This formula is a little trickier. I get this big ugly variable parameter. It is the integral of e to the integral p of t dt times q, which is t minus 1 plus t to the negative 1 dt. All of that times, oh, well, look at that. We just computed that guy. It's 1 over t squared. Okay. Up here, I had a negative out front. The only thing that changes is that I won't flip this guy over, so I will get t squared in here. So now I have the integral of t squared times t minus 1 plus t to the negative 1 dt. All of that, whatever I get, will be multiplied by t to the negative 2. Cleaning up my integrand, I get the integral of t cubed minus t squared plus t dt times t to the negative 2. And because I'm running out of room on my board here, I'm going to jump to the end result. I get t squared over 4 minus t over 3 plus a half as my particular solution. Now, the very last step is the fun one, because I get to just write the answer down. That y of t is just the complementary solution here, c over t squared, plus the particular solution, t squared over 4 minus t over 3 plus 1 over 2. Except that this comes with the caveat that t cannot be 0. So whichever interval of existence I would give, it just can't have 0 in it. But here is my general solution.